Last night we spoke to the last man on the moon.
And tonight we're heading to the centre of our galaxy in search of an object 4 million times the mass of our sun, crammed into a space smaller than our solar system.
I'm Brian Cox, he's Dara Briain, and this is Stargazing Live.
Welcome back to Jodrell Bank for night 2 of our 3 nights of Stargazing Live. Yesterday we concentrated on the moon, which is a little bit unfair because it didn't actually rise for a couple of hours until after we went off air. So we're relying on people either staying up late or getting up nice and early, and many of you did and sent us any number of photographs.
Yeah, I've got to show you some of these photographs. This is a beautiful picture of the moon, which was taken by James West from Chandler's Ford. We have another one here, which was taken by James Dyson.
James Dyson? Do we think it's the James Dyson?
James Dyson.
Is it?
I think it is, probably.
Okay,
And this picture, I'm particularly fond of. This is a beautiful picture of the Pleiades. The Pleiades is a cluster of young stars, so these were all formed together, young blue stars. Most people can see about 6 or 7 of them with the naked eye, but you can see tens of them with a telescope. It's a beautiful picture. And that's transient. In a few million years, that will drift apart. Well, a few hundreds of millions of years, it'll drift apart and it won't be a cluster anymore.
Now, we've had the most incredible response so far. A lot of you have contacted us, particularly about Captain Cernan. And some of you even wanted to know, and this is a bit of an old count, why did the Stars and Stripes flag look like it was flapping in the wind when there is no atmosphere on the moon? Now, settle this one once and for all.
This sounds to me like a conspiracy question. The answer is that there's a piece of metal in it because they knew it'd have flapped down because there's no atmosphere. If you still think we didn't land on the moon, turn over to ITV. I don't want you.
For those of you still here, yeah, keep those questions coming in to us by email, stargazing@bbc.co.uk, and tweet us using the hashtag #BBCStargazing. Now, you also join our online chat room, Talk Stargazing at bbc.co.uk Stargazing.
Now, last night we were able to get a great look at the Orion Nebula and prepare at Jodrell. So to see what's in the skies over Macclesfield tonight, it's over to Mark and friends, and I think a very special guest astronomer.
Well, good evening, everyone. Yes, I'm joined not only by a veritable army of astronomers from the Liverpool and Macclesfield Astronomy Society. How are you doing, chaps? They sound like they're having some fun. And of course, they've joined us for our special star party here at Jodrell Bank. And of course, you can find out details of the events that are around the country near where you are at our website, which is bbc.co.uk/stargazing. Now, standing relatively closely to his new telescope is impressionist and space buff John Coleshaw. So, John, welcome to us. What is it about astronomy for you?
Well, I remember receiving the Observer's Book of Astronomy by Sir Patrick Moore when I was 9, and I read it from cover to cover and was just hooked. And any time there's a clear night or the moon's out, you just can't resist to get out and have a look. And that's why I've got my new telescope and some ridiculously big binoculars.
Beefy pair of binoculars, I may say. Do you use them often?
Yes, clown binoculars. I haven't got a stand for them yet.
No, you do need a stand. Certainly binoculars like that magnify an awful lot.
Yes.
So you do need quite an impressive stand. Well, the skies are looking incredibly clear for a second night running. So come back to us later on and we'll show you what we've found.
Now, the skies are very, very clear. It's a fantastic night to see stuff. But ironically, the thing we're going to talk about mainly tonight isn't actually visible.
Yeah, tonight we're going to talk about black holes. Now, I get asked about them all the time in the pub. And the truth is that from a physicist's perspective, we don't really understand them. So here's an introduction to these enigmatic inhabitants of the cosmos. Black holes are some of the strangest, most mysterious and destructive things that exist in the universe. There's one here. And there's probably another one here. But you can't see them. And they can't be photographed. So we have to use computer graphics to try and explain what they are and how they're formed. Black holes are cosmic bodies with such immense gravity that nothing can escape them. And for their lives to start, a star has to die. Stars are effectively huge nuclear reactors fueled by hydrogen. At the end of their lives, when the fuel runs out, they die. When this happens, stars the size of our sun wither to become much smaller bodies known as white dwarfs. But when much bigger stars die, they destroy themselves in explosions known as supernovas. If the star is more than 30 times the mass of our Sun, black holes can be formed. As the outer layers of the star blow off into space, the core of the star, which can be as big as a planet, is crushed down to almost nothing. The whole process can take less than a second. What's left is an object that has the same mass as the core of the star, but is now packed into a much, much smaller space. But despite being significantly smaller, it still exerts the same gravitational pull. This incredibly powerful entity, which is small but massive at the same time, is what we've come to know as a black hole. From the moment of their creation, some black holes begin firing out great jets of radiation. The immense gravitational pull from the holes means that anything that strays too close to them is powerless to escape. Even a nearby star will be torn apart, the matter from its surface being pulled into orbit around the hole. That pull from the black hole is so strong that eventually it's impossible to escape, no matter how fast you travel. This terrifying point of no return is known as the event horizon. Everything in its path is sucked in, and the more it swallows, the bigger the black hole becomes. Beyond the event horizon, not even light can travel fast enough to escape. That's why you can't see them. And how they get their name, they're quite literally black holes in space. If by some miracle you were to survive the tidal forces at the event horizon and fell into a black hole, you'd be ripped apart. But nobody knows how long that would take.
So we're going to go to the very edge of physics in this show, and we're also maybe even go to the very heart of our galaxy. But it's a journey we should probably start, well, right here.
Yeah, let's take a look at where we are in our galaxy. So this is a picture of the Milky Way. Of course, it's taken from outside it, so it's a graphic. But that is the location of Earth in the Milky Way.
We had that as a question actually from Gary Getty in Belfast. How do we know where the Earth is in the Milky Way, and how can we know what it even looks like?
Yeah, I mean, it's interesting. There's something like between 2 and 400 billion stars in the Milky Way, and we know this structure very well. How? Because from there, you obviously can't see it all. Well, you use telescopes like the Hubble. You use radio astronomy. So there's a radio emission from hydrogen gas, which is all over the Milky Way. And by looking at that radio emission, you can see how bright the emission is, so how much hydrogen gas is. It doesn't get absorbed by all these stars and all the dust in the centre, so you can see straight through. Also, by looking at how that shifts, you can see how fast it's moving. So you can work out precisely the structure and the speed of rotation, actually, of our galaxy.
Now, when we look in the sky, every star we see is part of the Milky Way.
Everything in the northern hemisphere you can see with the naked eye, apart from one thing. And we've got a picture, I think, a live picture of that one thing. So this is from Macclesfield now. And where are we? This is a picture of the there it is, of the Andromeda Galaxy. So this is the nearest neighbouring galaxy to us. It's about 2 million light years away. There are something like 1 trillion stars in that galaxy. That's a live picture now from the field just over there of Andromeda.
And as a galaxy, the galaxy is basically like a collection, a clump of stars.
They are. And we've seen, that's the nearest neighbour, so that's 2 of them. I want to show you just one picture, which is one of the most famous pictures in all of astronomy, which is this. It's called the Hubble Deep Field Image. It's a picture of a piece of sky you would cover. Take a 5-pence piece and held it around 75 feet away, so let's say about 20, 25 metres. Cover a little piece of sky. It was a piece of sky that was empty from the surface of the Earth as far as we could tell, so uninteresting. But the Hubble Space Telescope in orbit took this picture, and you see it's far from empty. In fact, there are over 10,000 galaxies in this image. The most distant 13 billion light years away, so the light has journeyed through almost the entire history of the universe to get to us. And if you extend that over the entire sky, there are around 350 billion galaxies in the observable universe.
Now, although we can see the Andromeda Galaxy in the night sky, that's pretty much the only galaxy visible to the naked eye in this hemisphere. But there's much more on offer in the southern hemisphere, which is where Liz Bonin is standing by for us right now.
Thank you very much, Dara. Welcome to the Southern African Large Telescope in the middle of the Karoo Desert. The weather has been rubbish again here today, Dara. What can I tell you? Murphy's Law. But it looks like it might be clearing up, which is why the SALT telescope is moving into position, getting ready for a night of observations. Now, there are two galaxies that are visible to the naked eye down here. They're actually closer to us than Andromeda. And a couple of nights ago, I went galaxy gazing with some budding astronomers from the nearby town. In the middle of the Karoo Desert, about 200 miles northeast of Cape Town, lies the tiny town of Sutherland. Before the South African Astronomical Observatory relocated here in the mid-70s, this was just a small farming community with a few hundred people. And you show me where you live! You show me where you live! But now, Sutherland is home to one of the largest telescopes in the world, and that has made it something of a tourist destination. And astronomers are also keen that the whole community understand just what a special stargazing spot this is. Anthony Metis runs the observatory's outreach program. Okay, so what's happening with these kids this evening? You take them out to fly kites. Why?
Liz, one thing about the kites is you have to look up. It's a way of exposing them to the night skies.
So as the sun begins to set and the stars come out, they'll change their attention to...
They'll change their attention to what's happening. Sometimes we're lucky and we get a shooting star, and immediately somebody will ask, what just happened up there? You know? And we have actually one of the astronomers down here, David Gilbank, will be talking to the kids about galaxies later on as well.
A good way to describe a galaxy is as a city of stars. So basically our Milky Way is all the stars that belong to our star city. If we could see our galaxy from the outside, what we'd actually see would be something that looks like the shape of a dinner plate, something that looks like a disc like this. So we actually live about 2/3 of the way out from the centre. And so when we look up at the night sky, when we see this thick band, we're actually looking into the thickest part of the stars as if we're looking through the edge of the plate.
How many stars are in our Milky Way?
It's a good question. So there are about 100 billion stars within our own Milky Way galaxy. So that's a 1 with 11 zeros after it.
What is the closest galaxy to our own Milky Way?
Okay, so the nearest galaxy that's about the same size as us is called the Andromeda Galaxy. But there are actually lots and lots of much smaller galaxies in between. So if you look up here, you may be able to see that there's kind of this misty patch of light here, which kind of looks like a small version of the Milky Way.
Yeah. Can you all see that?
So this is called the Large Magellanic Cloud. And this is actually a satellite galaxy of the Milky Way. So in the same way that the Moon is a satellite of the Earth and orbits around us, the Large Magellanic Cloud is a satellite galaxy of the Milky Way and orbits around us. So what you're looking at through the telescope is actually, it looks like a bright patch within the LMC, and this is something called the Tarantula Nebula. It may look like little tendrils, like legs of a spider. This is a big cloud of gas in which stars are being born right at the moment. You can also see that there are new young stars in the LMC by looking around it, by looking at we see lots of bright blue luminous stars.
So new young stars are blue.
Yes.
Why is that?
If you think about, for example, the taps on your sink at home, you have blue being cold and red being hot, and it's exactly the opposite in astronomy. Okay. So the way to think about this, if you imagine taking a piece of iron and putting it into a fire and heating it up, it'll start off glowing red hot. So that's the coolest you could possibly get. If you heat it further, it will eventually start glowing white hot. And if you could heat it hotter without the metal melting, it would eventually glow blue hot. So blue is the hottest type of star, and red are cooler stars, but still very hot. So I can show you what I mean. Okay, so this is the LMC that we've just been looking at.
And that's the Tarantula Nebula there?
That's the Tarantula, yep. These very hot, very bright stars burn up their fuel very fast, so they don't stay around, they don't live very long. And so if you see these hot blue stars in a galaxy, you know that they've been put there recently, so they know that it's forming new stars. However, if there's no new star formation going on, then you'll only see these older, longer-lived stars which appear red.
And they're red because they're older.
That's right, yeah.
So what is it that stops star formation in galaxies?
So we know that in order to form stars, we need these nebulae, these star-forming regions, these clouds of gas. So we know that something must be removing the gas or preventing it from forming stars in some way. But we don't know exactly what that is, and this is one of the things that I'm trying to answer and work that I'm starting to do here with SALT.
And there is also a small Magellanic Cloud in the southern hemisphere. In fact, SALT altered its fixed viewing window to be able to observe it in its entirety. And it's below the large cloud, a little to the right. It's got about 1/10 of the stars of the large cloud, and it's actually more elongated than the large one. It's just that we look at it head on from Earth. Now, David, the Magellanic Clouds are part of this local group of galaxies. What is a local group?
So the local group's the name that we give to the collection of all nearby galaxies that are bound together by gravity. So the local group consists of 3 main big galaxies, including the Milky Way and Andromeda, and maybe several dozen smaller galaxies like the Magellanic Clouds and smaller.
Okay, and you've been taking part in a survey that's attempting to find out how many galaxies there are out there in the universe. You've looked at just 3% of the sky. What have you found so far?
So we're mainly looking for clusters of galaxies, so associations like the local group and larger. And so far we've found about 30,000 galaxy clusters, and each of those clusters contains maybe tens to hundreds of galaxies.
That amounts to already 3 million galaxies in just a tiny speck of the sky. Galaxies are everywhere that you look, and apparently they're distributed across the universe in a great cosmic web of filaments, and astronomers are only just beginning to understand what that might look like. Now, join me later when I find out how galaxies grow. Apparently the Milky Way is in for a bumpy ride.
Thank you very much, Liz. Now, here's a positive message for all of you thinking you need more exercise this January. In this universe, there is no such thing as being at rest. Even as we spin around the sun, the entire solar system is itself spinning around the Milky Way.
Yeah, if you think about it, we travel around the sun, of course, once a year. That's 67,000 miles an hour on average that we're travelling now. But the sun is one of 200 billion stars in the Milky Way galaxy. So our whole solar system is in orbit around the galactic centre. And it takes about, we think, 225 million years to make one orbit. Now, if you think about that, that means that since the formation of the solar system, we've made about 20 orbits. So that's, 20 galactic years, if you like. And I think the most remarkable thing about that, if you think humans have been around for a long time, we've been around for 1/1000th of a single galactic year. That's like one afternoon.
It's all fairly astonishing. What always amazes me is these levels of clustering of order. We're going to get to some explanation of how that happens. But first we're going to go out into the field and see how Mark is doing.
Well, the skies are still miraculously perhaps clear for us, and the guys have been finding some beautiful objects in the sky, including the Andromeda Galaxy, which is almost straight above us now, just above the constellation of Pegasus. Now, John, I know you're relatively, well, you're not that new to astronomy, are you? But you've just got a telescope recently, and you've had some views through it so far tonight.
Yes, we saw Andromeda through this Dobsonian here, and just spectacular. And it's sort of a little bit of cloud went across, and almost, cloud can be slightly helpful sometimes if it takes a certain amount of glare off.
But not too much.
Not too much. No, exactly.
And when was the first time you saw a galaxy? I mean, you've seen galaxies before tonight, I assume.
Yes, I've seen Andromeda. I think the first time was probably in the 80s. I think my favourite view of our galaxy, the Milky Way, was I saw in Kenya a few years ago, far away from any kind of light pollution. And we've got a wonderful polished clear sky tonight where you can make out individual stars. But under those conditions, it's breathtaking, just the cacophony of light.
Beautiful to see.
Yeah.
Now, of course, unfortunately, it seems that up to 2/3 of Western Europe can't now see our galaxy because of light pollution, and that's basically excess or intrusive light which brightens the night sky. Now, on your screens is a view of Europe that was taken from the International Space Station, and whilst it does look pretty spectacular, all that light is actually the glare from street lights, from offices and from houses. Now, the effects from all this excess lighting are quite plentiful. Now, there's an effect on the environment. Of course, it wastes vast amount of money as well. It can disturb the wildlife, and it can even affect your own body clock. But more crucially, it's disastrous for astronomy. Take a look at this.
I've come to the Royal Observatory in Greenwich, one of my favourite places and a real landmark of British astronomy. I'm here to meet a group of stargazers who all live nearby in London.
Sujit, nice to meet you, Sujit. How are you doing? Trevor.
I want to know about their experience of astronomy in the city and find out how they're affected by light pollution.
Jamie, how are you doing? So, Sujit, what is it that you find frustrating about light pollution?
It's just the glow, really, the glow in the sky that prevents me from seeing the things I want to see. you know, particularly when I'm with my children, because they see all the images in books and on the TV, and the question I get asked is, well, why can't we see things like that? And clearly the answer is because of light pollution.
It's constant, really. Your eyes never get adapted fully to the night sky. Security lights activating by animals in gardens, it's constantly flashing. And of course, street lights are a major problem.
Almost completely robs you of the fainter stars, and some of the brighter stars you can't even see close to the horizon because there's this constant orange glow. It's there all the time.
When Greenwich Observatory was first founded in the 1600s, it was a long way outside the centre of London. But now it looks straight out over the city. And all these lights, from the Millennium Dome to the individual street lights, have blocked the sky from view. As London astronomers, these guys rarely get to experience proper darkness. So I'm going to take them somewhere to see what the stars are like without the orange glow.
We're going to take you guys to a proper dark sky. What kind of things are you looking forward to seeing?
I would like to see a naked eye view of the Andromeda Galaxy, which people say is possible, and that would really make my day, absolutely.
I'm longing to see the Milky Way. Just love seeing it on photographs. It's absolutely beautiful. So just to see that with my own eyes, be a dream, really. Really would.
And how about yourself, Jamie? What are you looking forward to seeing?
Dying to see a galaxy. Any galaxy will do. Just being able to see it with my own eyes in real time. It's something that's just so far away. It kind of would wow me, I think.
So, to fulfil the wishes of these city astronomers, we're leaving the bright lights behind and heading somewhere really, really dark.
Now, we've come all the way from London.
Yep.
Been diligently keeping your heads down to the ground.
Yep. Suspense is...
3, 2, 1. Have a look. Wow. How's that?
Beautiful. It's amazing.
There's just so much there to see. Just so many stars. It's overwhelming. It is disorientating.
Lovely.
Beautiful.
This is the Rollright Stone Circle in the Cotswolds. It's so dark here that we have to use a special light-intensifying camera that's thousands of times more sensitive than any normal camera.
So now, can I tear you away for just for a moment? I know it does look pretty impressive, and I know you're not used to it and you want to make the most of it, but I've got a challenge for you.
Okay.
You're going to have to work for this. But the challenge, can you see, if you turn over in that direction, I'm going to use my laser pointer now, just up there is the constellation of Pegasus. It's the winged horse,
yep.
But it's the big square of Pegasus that we're interested in. You see that just there?
Yes.
Yep.
I'm guessing you could probably pick out those stars back in London, just about. They're
Yep.
just about. Your challenge is to count how many stars you can see in the square of Pegasus.
Really?
Yes.
I can't normally count any inside it.
Well, I can't normally.
See one.
So normally from London you can't see any. Okay,
No.
right.
1, 2, 3, 4.
2, 3, 4, 5, 6,
but
7,
I'm not older than
8,
you,
9,
Jane.
10, 9,
11, 12. I've got 12.
You've got 12.
Yeah.
How about
At the
you, Susie?
moment.
You on 12 as well?
I've got one out, it might be discrepancy, it's on the line.
Okay, borderline whether it's in the square or not.
12.
We'll say it is. We'll just say it. So if you can see 12 stars within the square of Pegasus, that's a fantastic measure of how dark a sky is.
That's amazing.
And to be able to see 12 is incredible.
And 0.
Yeah.
And 0 from London. So it makes you realise just the beauty of what you get.
Wow.
Now I've got a bit of a treat for you. If we take the top corner star off the square of Pegasus, and then we hop across from that one to that one up there, and then we hop further over to the north, there's one star there and then another faint one there. Can you just make out a fuzzy blob?
Yeah.
Just about there.
Yeah.
Yeah? That is the Andromeda Galaxy. Mind-blowing, isn't it?
Yeah.
It's really amazing.
Now, we've seen some pretty incredible things so far, but the crowning glory, the thing that I'm pretty sure you wouldn't get to see normally from your homes in London, is that overhead. Running all the way from the horizon over there, the Milky Way. You see it? Yeah.
Absolutely.
Fantastic.
Yeah. Incredible.
And that is actually the combined light from all the stars in our galaxy. And as you can see, there's thousands and thousands of them.
Even our specialist cameras aren't sensitive enough to pick up the Milky Way, but here it is in all its glory, taken on a long exposure from exactly where we're standing.
I can't believe I'm seeing it with my eyes.
It's quite incredible, isn't it?
Yeah, yeah.
It's coming out really nicely.
It really takes a moment to take it all in.
Yeah.
Seeing it on
overwhelming.
pictures for all this time, and there it is.
I'm awestruck because I've never seen so many stars in such clarity. It's just awesome. It really is. Just never seen it before, which goes to show the beauty of the night sky is taken from us by light pollution.
It's incredible how much more you can see in the correct conditions. Dark Sky Discovery is a network of groups who have put together a list of dark sites across the country so you can find the best places near you.
And they don't have to be in the middle of nowhere. We've got some images here for some of the sites. This one, for example, is the Insect Science Centre. So see, it's pretty built up. It's in Winchester in Hampshire. And this is the picture that was taken from that site. It's a stunning picture. And then we've got the Milky Observatory in Northumberland. And again, there's some star trails there from the site. You see, beautiful seeing a North Star, of course, with all the star trails rotating around it, or appearing to as the Earth rotates for the pedants. Yeah. Here's Waterworks Nature Reserve in Lee Valley, London. Again, beautiful dark sky. And finally...
This is by far the best. We're looking at
this is great. Knockbrett Primary School car park on the Isle of Skye.
The Northern Lights.
A spectacular picture of the aurora. The sun's very active at the moment, actually, so if you're in the north of the UK, you have a good chance of seeing something so beautiful.
If you want to find the closest place to you, all the information, as ever, is on our website, bbc.co.uk/stargazing, words I'll be saying in my sleep for months after this show. You will also find details of how to nominate an area as a dark sky discovery site. It doesn't have to be dark enough to see the Milky Way. What you're looking for is an area away from the direct glare of bright streetlights, buildings or cars, and with a clear horizon.
Now, light pollution isn't just emitted from office blocks and city centres. We're all guilty of it. Even the smallest communities produce a heck of a lot of light.
So tomorrow night, we're going to attempt to get an entire population of a town to switch off all their lights simultaneously live on air. Here's the lowdown on what we're going to try to pull off.
This rural town may not be the kind of place you'd associate with light pollution.
Only 1,600 people live here, and it's next to an area of Exmoor that has some of the darkest skies in Britain.
But that's precisely why we've chosen Dulverton for this challenge, because even a town as small as this generates a lot of excess light.
As the sun goes down, the lights come up, and a familiar orange glow descends on the centre of Dulverton.
We should be able to see the Milky Way from here, but like 90% of the UK, we can't.
So we decided to get every single person in Dulverton to turn off every single light in town.
And last week we sent Mark down there to help make it happen.
With 720 houses, 177 streetlights, 40 shops and cafes, 3 pubs and a sports ground, there was plenty to do.
There are literally thousands of lights here, and it's going to take some pretty serious powers of persuasion to get everybody on board with this.
There are also quite a few technical hurdles.
As it turns out, most of the streetlights are controlled individually by automatic light sensors, so there's no great big button that we can use to turn them all off.
This challenge won't be easy, but if it works, it's really going to bring the community together, and we might even get to see the night sky as nature intended.
So for the last couple of weeks, Mark has been trying to spread the word amongst the inhabitants of Dulverton. How's that going, Mark?
Well, it's been a challenge, I'll say that, but the guys in Dulverton really seem to be getting on board with it. We've had posters and flyers put through letterboxes, and we've even had some of the shops put special displays on, including a space cake. So they really seem to be up for it.
They probably think you're utterly weird, but what do you think the chances are of success?
It's difficult to know. You know, we need everyone to do this. We can't just rely on the council to turn the lights off or the shops to do their bit. We're reliant on absolutely everyone doing their thing. So until tomorrow night, we just don't know.
So as soon as the show finishes tonight, Mark will be hot-stepping it down to Somerset for a final day of persuading the townsfolk before coming live from Dulverton itself for the big switch off tomorrow night. If you're from Dulverton, he's legit. The man is not attempting some hideous mass burglary heist. He's definitely going to do this.
Don't chase him out of town. Take that wicker astronomer down. It's fine.
Now, aside from the amazing array of planets, stars and galaxies that are up there to photograph and enjoy in the sky, occasionally things crop up that don't immediately make sense.
Yeah, take a look at this picture. Now, if you think this is a UFO, you should already have turned over to Celebrity Big Brother. But, however, let's have a look at it. Actually, having said that, my little machine, there it is.
Look, it's not bad, though.
It's not bad,
except for the poo. Except for the poo, yeah, which the seagull is dropping behind him. This is the giveaway bit. UFOs generally don't poo. And they don't have wings and a beak. Yes. Even here at Jodrell Bank, about 30 people call every year to report seeing an unidentified flying object. So how come so many of us are seeing things?
There are some things that just seem to belong in a Hollywood movie, and not in an A road in Wiltshire. But here's a surprising statistic. 1 in 5 Britons are convinced aliens have visited Earth. In fact, the government took sightings of UFOs sufficiently seriously that until 2009, the MOD had a department investigating them. Over 11,000 cases were examined by MOD staff. David Clark has been studying them, and he wins the prize for Best Job Title of the show.
You've got reports from police officers, coast guards, pilots, military aircrew, and some quite silly reports from people who'd seen things whilst leaving the pub and that kind of thing.
Amongst the thousands of sightings, a couple stand out. In 1996, in the Boston Stump case, a strange light was spotted in the sky above Skegness in Lincolnshire.
It was made all the more credible by the fact that the key witnesses in this case were police officers. In the end, one of the police officers went onto the top of the police headquarters in Boston with a camcorder and started making a film.
The police alerted the RAF, who saw an odd blip on their radar which stayed there for hours. The UFO caused such a stir, the newspapers had a field day. Another strange case was that of Alex Birch, who took this photograph in Sheffield.
The photograph was examined by intelligence officers, and there was a full report that was produced on this. Quite something for a 14-year-old lad in the 1960s.
By an eerie coincidence, Alex was privy to another UFO sighting where he took this photograph more than 40 years later of Retford Town Hall in Nottinghamshire.
When he got home, he was looking at the negatives and he couldn't believe it. On one of the images, there's a classic flying saucer by the side of the town hall.
So it's clear that many perfectly normal members of the public are spotting UFOs all over the place. But not everyone is convinced that they have anything to do with aliens visiting Earth.
There are many, many things that we don't fully understand about the atmosphere. Just because you don't know what something is doesn't mean it's a flying saucer or an alien spacecraft. It may just simply be something we don't understand.
Also, to expect aliens even to reach Earth is asking quite a lot.
Most people have very little idea of the enormous distances between the stars. We're talking light years. At our current rocket speed, it would take tens of thousands of years for our own spacecraft to go outside of our solar system and reach another star system. And we've no reason to believe that there will be any sort of civilization within many, many light years, maybe many hundreds of light years of Earth.
So if we're not seeing aliens, what are we seeing? Well, in the case of the Boston Stump, it's all rather embarrassing.
They consulted the Royal Greenwich Observatory about the lights that had been seen in the sky, and their opinion was, from the directions and the times that they'd been seen, that what the police had actually observed was the bright planet Venus, which was really prominent in the sky at the time.
To be fair, this is quite a common mistake. Venus is known as the queen of the UFOs because it's so often mistaken for something more mysterious. An in-depth analysis of Alex Birch's photos concluded his flying saucers were most likely ice crystals in the atmosphere. and the one he saw years later in Retford was possibly caused by a moisture droplet on his camera lens. Some of our UFO sightings are also a result of us spotting the latest military hardware.
World Air Forces are always experimenting with new aviation technologies, and that these can sometimes be as much as 10 or 20 years ahead of what they see in the news. I think my favourite is the NASA Satelloon, which was launched in about 1960, 1961. And this was an absolutely vast spherical metal balloon that was released into the upper atmosphere and was used to bounce communications from one part of the world to the other.
For decades, the military have been flying exotic objects around the sky, and they're still doing it.
So by the 1980s, much of the US Air Force's sort of technological research was going into stealth aircraft and the enormous stealth bomber, the B-2. By the time that the stealth aircraft had been publicly revealed, it was probably no coincidence that the general trend in UFO sightings was moving away from the circular disk towards something that was more triangular in shape.
And a lot of UFO reports are down simply to people not knowing what's in the night sky. Satellites, for example.
Well, there's a group of satellites called Iridium. They're communication satellites in very high orbits, and most of the time you don't see them, but every so often they just catch the sun's light for maybe 10, 15 seconds. And anyone looking at that, seeing it get brighter and brighter, might well think this was something coming straight towards them, and then as it faded, they might think it had turned around and whizzed away. But in fact it's not, it's just that satellite going across the sky, just catching the sun's light for a period of 10 or 15 seconds.
So satellites, water drops, planets, secret military planes, that's that settled then, eh?
I think no matter how many cases you explain, people will always be seeing something new and coming and asking for an explanation. So I don't think that UFOs will ever really die.
We may mention more about UFOs and aliens tomorrow. One quick apology, though, on behalf of my colleague here. Celebrity Big Brother doesn't start until 9. So he's not the professor of everything. Earlier on, Liz Bonham got an amazing view of the closest dwarf galaxy to Earth, the large Magellanic Cloud. Now she's moved to a larger telescope to get a much more detailed look.
Thank you very much, Dara. We are in the control room of SALT with Petri Väisänen, who we met last night. Petri, you're a bit of an expert on galaxy evolution. Tell me what that SALT image is there.
Just a little while ago, we were looking at this interacting, colliding galaxy about 400 million light years away.
How big is it?
It's a major galaxy. It's smaller than the Milky Way, but much bigger than the Magellanic Clouds, for example.
Okay, so how do galaxies get that big? How do they grow, Petri?
They basically grow by accumulating smaller galaxies around them, eating up, gobbling up other galaxies. And the bigger the galaxies, the faster it will grow. So there's little galaxies coming onto bigger ones, but then there's also bigger galaxies interacting and colliding and merging into even bigger ones.
Okay, so this image is of colliding galaxies, is that right?
That's right, this other one over here. There's two major galaxies there and a smaller one in an interaction. And basically collision. But within the collision, the individual stars inside don't actually collide at all.
Why not?
They're just too far apart from each other. They're very small.
Okay.
But all the gas and dust inside, that collides. And when it compresses, that's when new stars are being born. And the more violent the interaction is, like in this case, the more spectacular of a starburst you get.
Okay, now it's a beautiful image, but you're interested in more than that, aren't you, Petri?
Yeah, for example, here at the SALT, what we do with this kind of galaxies, you would take spectra. So from the spectra, that's where a lot of the science comes from. We can measure masses and their star formation histories, basically try to piece together where did they come from, where did they go, how do they change, galaxy evolution.
Fascinating research. Thank you very much, Petri. If you follow me to this screen, another SALT astronomer here is Steve Crawford. Steve, I believe the Milky Way is on a collision course with Andromeda, is that right?
That's true, Liz. The two galaxies, the Milky Way and Andromeda, are expected to merge together in about 4.5 billion years.
Okay, so not too soon, but what exactly is going to happen between the two galaxies?
Well, if we take a look at the simulation here, we can actually see these two spiral galaxies merging together.
So say that's the Milky Way, say that's Andromeda, they're literally going to pass through each other. So what's going to happen to our solar system and planet Earth?
Well, it depends on where in the Milky Way the solar system is. It could either be driven into the center of this new galaxy or flung out into deep space.
Wow, okay. And what will be the resultant galaxy? Will it look anything like the Milky Way or Andromeda? Will it be completely different?
Well, these two spiral galaxies will actually form together to make a new elliptical galaxy.
Okay. And what are we going to call it? Are we going to call it Milkomeda or Androway? What do you reckon?
Well, with all the action that's going to happen when these merge, I might go with Andromeda's milkshake.
That's a really good name. 4.5 billion years away. Don't think we have to worry about it quite yet. Thank you very much, Steve. Now, coming up tomorrow, I'm going to go right across the plateau to check out this. It's called Super WASP, Super Wide Angle Search for Planets. It's already found 75 exoplanets and is actively looking for more as we speak. I'll be finding out exactly how that works tomorrow night. I will see you then.
Thank you very much, Liz. We'll also find out tomorrow how our search for a planet has gone. Don't forget about that. Go onto the website. Let's go back first, though, to our dark field and see how Mark and the observers are getting on.
Well, John's had a great time out here tonight, but he's had to head back into the studio for Back to Earth later on. But the skies are still, for the second night running, clear, which is remarkable. But the guys here have had a great time. They've been taking some beautiful images. And joining me now is Steve Warbis from the Macclesfield Astronomy Society, who's taken a beautiful image of the Messier object. So, Steve, can you tell us a little bit about it, please?
Yes, it's an assembly of 109 of the 110 Messier objects, because one of them is never visible from my back garden. They're a mixture of galaxies, star clusters and nebulae. As the seasons have rolled by, I've made a conscious effort to try and capture the more obscure ones in a digital camera, usually attached to a telescope. And whilst my sky conditions are quite orange and challenging, overall, hopefully I'm quite pleased with the result.
And from the back garden, that's just incredible. Now, stay tuned for Back to Earth, where I've got a special star guide to show you what you can find in the night sky, including the Andromeda Galaxy. But for now, with that all-important weather forecast, here's Matt Taylor at the BBC Weather Centre.
Thank you very much, Mark. Well, the clearness and clarity of the sky the past few nights has been a real treat, but things slightly different tonight. Really disappointing night for stargazing in Scotland, Northern Ireland. Thicker cloud has spread in here. Cloud you can see across England and Wales, though initially it's just some high cloud dulling the sky in one or two spots. So it's a case of you will have to get out there quite quickly across eastern Wales, central and eastern England, because quite quickly through tonight we're going to see those cloud layers you've seen in Scotland and Northern Ireland spread their way southwards and eastwards, bringing with it mist and rain to the most part. But by the end of the night, for the early rises, before the sun gets up, you might get some clear skies into the northwest of Scotland later. So it is a case of get out early if you can for tonight, but tomorrow we split the country into two. Best of the weather will be in the north. Southern parts of England and Wales, a lot of cloud again with outbreaks of rain. North Wales, Midlands, East Anglia, you might get a clear view of the sky initially before the cloud thickens up. It's really Northern England, eastern parts of Scotland and Northern Ireland which you see the best of the clear skies come and go throughout the night. I'll have more on that though tomorrow. For the time being, it's back to Dara and Brian.
Thanks, Matt. Now, one of the biggest questions is how the Milky Way was formed.
To help us find out, we asked Oxford University to do something that they've never done on this scale before, which is to run a computer simulation to show how, starting from the beginning of time at the Big Bang, our galaxy formed. Here to show us the result is Dr. Andrew Ponson. Doctor, how are you? This is not a simple task.
No, it's not. So we start by programming a computer with some basic physics, mainly gravity. It needs to understand how gravity affects things, and some gas physics. It needs to understand how gas changes. And then we set up the computer with what we think the universe looked like near the Big Bang.
So basically, you said the basic laws, and you press go, and you leave it to run.
That's basically it. Yeah.
And this is basically the input is from the cosmic microwave background, so the earliest light we can see in the universe. And we look at what the universe was like about 380,000 years after the Big Bang.
Yeah, and it had tiny ripples in it, which we think came from quantum processes right at the start.
Yeah. So this is the beginning of the simulation.
Yep.
So we're at. Well, that was the beginning, and then we passed 380,000 years or so. Yep. That's where the cosmic microwave background was. And then talk us through what we're seeing now.
So what you're seeing is the matter that started out being quite uniformly spread out is starting to clump. So as well as the whole universe expanding, it's actually forming clumps out of what was originally quite smooth.
So what's the green?
I've coloured it green because it's actually dark matter. So normally you wouldn't be able to see it at all. It would be dark. But we can, of course, pick out anything in the virtual universe. So we've picked it out in green.
Now, so we should look at this. So we've frozen 1.7 billion years after the Big Bang there. And dark matter, we should just talk about that a little bit. So the universe is far as we can see, is dominated by stuff that isn't this.
Yeah, something like 4/5 of the stuff we think is not like the stuff that you and I are made out of, that the planets and the sun are made out of.
And we don't yet know what it is, but we can infer its presence. We're fairly certain how much there is there. Right? That's a solid observation.
We can measure that. For instance, through the cosmic microwave background helps us with that.
So what we're seeing there will be the visible matter, the matter we're used to, this kind of matter.
Yeah.
That's what we see there.
Yeah, that's right. So we've switched now, and the faint blue stuff is gas, and the white stuff is stars.
As a matter of interest, if you didn't run this with the dark matter in the simulation, would it work?
No, so you certainly wouldn't see this. Galaxies wouldn't form. There wouldn't be a big enough gravitational pull to pull the galaxies.
So we need the dark matter in order to create the galaxies.
So now we can roll the clock on again. So we're going to go on from.
I think we're keeping the clock frozen for the moment. We're
just
flying
show
in
us
the
zooming in
simulation.
now. Yeah.
You can see that these blobs that might have initially looked like single stars are actually tiny little mini galaxies, and they've each got maybe 10 or up to 100 million stars in them at the moment. And as we pull out again, bring the dark matter in, you can see that all of these are surrounded by big, what we call them halos of dark matter.
So we've got these irregular shaped galaxies in the simulation. They've already formed, and they've clustered around the dark matter, so the real matter's inside the dark matter, as it were.
Yeah. So when we carry on seeing what happens next, the dark matter is really going to control all this, although you can no longer see it. And what you see is these little mini galaxies all merge together in turn. And what is particularly notable about this process is that it carries on going. So it's not like a few mini galaxies come together and that's a galaxy. It carries on happening.
So this is basically the history through time of how our galaxy, which started as a small clump, then mashed in with other ones, they all span around each other to create larger and larger galaxies, until eventually we get up to now, where we're in the, now at 14 billion years.
Yep. So if you skip to the present day, you can see that it looks somewhat like a normal spiral galaxy, and you can fly in and see what it looks like from inside.
Now, what I find remarkable about this, so just to recap, it's a simulation of the evolution of the universe. So you input some basic things, basic physics, some basic data about the distribution of dark matter, and you press go. You sit there, and that galaxy emerges. It looks like the Milky Way, and this is a picture of the real Milky Way, and if we crossfade them, you can see that it's remarkably similar.
Yeah, I mean, it's a testament to the power of what we know in just some basic physics that we can do this.
I think that's remarkable.
Astonishing.
So that's the simulated Milky Way, and that's the real Milky Way.
Right.
Now, are we leaving out anything in this model? I mean,
yeah, I mean, there's certainly stuff that we don't fully understand at the moment. For instance, we have in there black holes in the centre of our galaxies, but we don't really understand fully what we're doing with those black holes.
Yes, they remain one of the big unknowns in galaxy formation, the role of black holes. That's not helped, of course, by the fact that no one has actually ever seen one. So how do we know for sure that they definitely exist?
Ask any physicist about black holes, and they'll tell you that they exist.
But I could say, there's a unicorn in these woods, and you would rightly say, no, there isn't, because I can't see it. But I could reply, yes, there is. It's there, but it's invisible. And you would probably think that I'm daft at best. But what's the difference between my imaginary unicorn and a black hole? See, black holes, by definition, are invisible. You can't see them. So how do we know that they exist?
The first clue that black holes are real came from here, in the Cambridgeshire countryside, in the 1950s. While the rest of the country were listening in to wireless radio at home, out here they were listening in to a different radio signal. Radio signals from outer space.
This is the Maillard Radio Observatory. Back in the 1950s, some of the first radio telescopes in the world were built here. And when they turned them to the skies, they heard this.
That loud hiss is the telescope passing over a strong radio signal in the sky, but they couldn't work out what it was or where it was coming from.
Now imagine this torch is that radio source sending out a beam of radio waves. So radio telescopes in the 50s could detect radio sources in the sky, and they could tell roughly where those beams were coming from, somewhere over there, but they couldn't tell precisely. But then an astronomer called Cyril Hazard had a very clever idea indeed. You see, he knew that on the 25th of August 1962, the moon was going to be in the same patch of sky as the radio source. So he just watched and he waited, and he saw that as the moon travelled across the sky, it went in between the Earth and the radio source and cut the source off. And then, as the moon continued its journey across the sky, the radio source reappeared. So, by measuring precisely when the beam disappeared and appeared, Hazard was able to pinpoint precisely the source of the beam.
It was tracked to what looked like a faint star in the constellation Virgo, just one tiny dot of light among the millions of others in the sky.
This is an image of that piece of sky, and that point of light just there is the source of the radio signal. Now, pretty much every point of light you can see in this image is a star inside our galaxy, inside the Milky Way. But this point of light, the origin of that radio signal, is 3 billion light years away, and yet it can still be seen. No star could shine that brightly. So what could that possibly be?
The astronomers called it a quasi-stellar object, or quasar for short, because they didn't think it could be an ordinary star. But black hole theorists knew of one way that stars could appear that bright, and that's if they were falling into a black hole. Stars falling into a black hole would be completely ripped apart. Gas and dust would be torn from their surfaces as they spiraled inwards at tremendous speeds, and emit so much radiation that it could be seen right across the universe. And that means we could detect it here on Earth.
So what the astronomers here in Cambridge realised was that that quasar they were seeing was actually a black hole, a giant black hole, and the light and radio waves was coming from whole stars having gas and dust ripped off them and spiralling to its destruction inside the black hole.
Over 100,000 quasars have now been discovered. All are thought to be supermassive black holes actively feeding on stars. And all of them are found in exactly the same place, right in the centre of galaxies. So does that mean that there's a black hole at the centre of every galaxy?
Our galaxy, the Milky Way, couldn't have a quasar like the one discovered here in Cambridge at the centre because we'd see it. It would shine as brightly as the full moon. It'd be visible in the daytime. But imagine a black hole that's eaten all the nearby star systems. So there's no gas and dust to spiral in, and therefore there's no radiation to make it bright. So it could still be that there is a supermassive black hole at the heart of the Milky Way.
One group of scientists spent 16 years painstakingly searching for it. And this is what they found.
This is, I think, one of the most remarkable graphics in recent scientific history. It's a picture of the centre of our galaxy and the stars that orbit around it. They're known as the S-stars. Now, the inner 2 stars you can see there are orbiting very fast around some central object. Actually, they reach speeds of around 11 million miles an hour. And when you plot the orbits out that precisely, you can calculate the mass of the object they're orbiting around. It turns out the mass of that object is 4 million times the mass of the Sun. But there's more than that, because you can also work out the maximum size it can be, because the inner S-star gets as close to that central object as Neptune gets to the Sun. So here we have an object 4 million times the mass of our Sun, compressed into a space smaller than our solar system, and it's invisible. The only thing that could be is a black hole at the centre of our galaxy.
Black holes started out in physicists' imaginations, but we now have evidence to prove that they're real. And not only do black holes exist, but we now suspect that they form the heart of nearly every galaxy in the universe, including our own.
Somewhere up there, we know there is a supermassive black hole at the centre of our galaxy, and it's that our solar system is orbiting around. So why are we going around a black hole? Why do we orbit around? To explain that, we kind of have to explain how gravity works. And this was something that Einstein's theory of relativity, general relativity, showed us. It shows us that gravity wasn't just an interaction between a planet and an object. It was the interaction between the planet and how it twisted the space around it. This is traditionally shown by physicists by using spandex like we have here.
I wonder where my trousers are going.
Yes, and you can see that a large mass, it twists the space around it. So there's something going past it is dented off course.
Yeah, essentially what Einstein said was things all follow a straight line through space-time. This is actually space and time. Masses curve space and time. So if you don't know that the space and time is curved and you're travelling through it, then it will look to you like you've curved around the mass.
And if you enter this dented space at the right speed, you'll end up just spinning round and round and round, and that's what an orbit is.
So I think the way you can think of gravity in Einstein's picture, it's a fictitious force. It's the result of space and time being curved by massive objects. So the question is, what happens if you put something very massive?
Incredibly massive. This is, say, for example, the curve you'd get off a planet, right? This is a black hole, and our fantastic demonstration here is the black hole just curves space so far that when something approaches it...
Yeah, so this could be, for example, a photon, a particle of light. What happens near a black hole is that the photon approaches and it can't escape when it crosses this boundary, which is called the event horizon. And what Einstein's theory predicts is as you get very close, actually right up to that thing, the centre of the black hole, which is called a singularity, infinitely dense, infinitely small, space and time are infinitely curved, and the theory itself breaks down. So this is probably the most fascinating thing about black holes from a physicist's perspective, is that Einstein's theory of gravity, the best theory we have, predicts its own demise somewhere down there.
And obviously now, spandex can't really stretch as much as space can. If it's infinitely dense, those sides go straight down. There's no way out for anything.
Yeah,
it just
you'd
goes
have to travel
like a waterfall,
much faster than the
straight
speed
down.
of light.
Now we're going to bring back in Tim O'Brien. He's the associate director here, and the study of black holes is one of the specialisms of Jodrell Bank. We can't see black holes, of course, but we can see their effect.
Yeah, welcome back, Tim.
Yeah. This is actually the Milky Way, seen with visible light, so that's the light of billions of stars.
Yeah.
But if we look at it with a radio telescope...
So this is with the Lovell telescope and others?
This was the Lovell telescope, the Parkes telescope in Australia and the Effelsberg telescope in Bonn.
Right.
So this is a radio image of the sky. Here we can see through the dust clouds that block our view of the centre of the galaxy. And right in the middle there, that bright spot, is Sagittarius A. It's where the black hole is
So that's
hiding.
what we saw, the S stars orbiting around on the film. But now, unlike this is the new research, essentially.
Yeah, so we just last week, actually, we just pointed our E-Merlin telescopes at a quasar. The quasar's in the middle of there. This is the optical view, that blue dot in the middle. And if we zoom in with E-Merlin and have a look with a radio image, what we see now is where the black hole is the bright spot in the middle, but this thing that shoots off to the left here is a jet of particles that's whizzing out from the region around the black hole, almost the speed of light. It's coming almost directly towards us, but the shape of it sort of indicates it's like a sort of corkscrew. So it's sort of spinning around like that. And one way in which that might happen is if this is the result of a merger of two galaxies. So each galaxy sort of brings its respective black hole to the party, and when the galaxies merge, the black holes end up whipping around each other, and that causes...
And will they fall into each other over time?
They will, eventually, yeah. They're actually going to be spiralling closer and closer together. They'll be producing gravitational waves, ripples in space-time, predicted by Einstein. Not yet directly detected, but actually we're working on that with this telescope and others across Europe looking at pulsar observations.
You know, I think one of the most remarkable things about these images, these experiments, is that we're trying to look for a breakdown in general relativity, and we're trying to look for a breakdown in Einstein's theory. For me, this is what science is all about, I think, because we're trying to test our theory to destruction.
Yeah,
beautiful.
Now, we have longer to discuss this, by the way, because this show feels like it's ending, but actually it carries on in this very, very room. We have another half an hour in which we can answer these questions and more questions. Don't forget, though, that we need your help to find our own exoplanet. Over 60,000 of you have taken part so far, and the more of you that take part, the better, the more likely we'll find the thing. That dress again, have it tattoo it to my head, bbc.co.uk/stargazing, where you can download this year's Star Guide and find links to the Open University's virtual planetsphere.
Yeah, now don't forget, we're going off air now here, but then we're coming back on air in about 10 seconds to go and sit there in order to carry on this conversation. We're going to be talking about black holes, of course. If you've got any questions, you can tweet those and send them in. We'll answer those. We're going to have John Culshaw doing an impression of me, staring wistfully at the sky as if I wasn't enough for you.
Listen, there are clear skies out there, so do go outside and have a look. We'll be back also tomorrow at 8 o'clock with more stuff. We'll see you then. Okay.
See you later.